Now, we will talk about the electrophoresis of colloid particles. Now, electrophoresis basically the electrokinetic transport of charged particles in a electrolyte medium or polar medium. So, that is the thing will be considered. Now, how this electrophoresis occurs? Now, we can define the electrophoresis refers to the motion of a charged colloid scale particle in an electrolyte solution under an applied electric field. Now, when a charged particle maybe let us take it as a sphere. Now, basically these colloid particles means its size will be of approximately some micrometer order, on the order of some micrometer, few micrometer, or maybe even a nanometer scale. So, this kind of particle. So, whether we consider it as a spherical, we can treat this kind of rigid particles as a spherical particle. So, there is not a big harm on the form of the surface is not going to make much difference because of the small scale size of the particle. So, we can treat it as a spherical particle, that is for the sake of convenience of our theoretical analysis. Now, what will happen if when we place a charged particle in a situation, say in a charged particle, we place it in a say negatively charged particle. So, the particle have a negative charge and we apply a say electric field like this. So, the particle will be in a electrolyte medium. So, there are charges, free charges. So, since the particle is negatively charged, so positive charge will be attracted close to the particle. So, there will be a formation of Debye layer, and these negative ions, positive ions, all will be in the electrolyte, which may be very close to this particle. So, there will be a imbalance of ions, but as we move away from the particle, so these ions are all balanced. Now, when you apply an externally applied electric field, say let us call it a constant electric field E0. So, what will happen? This particle will be attracted to the, since it is negatively charged, so it will be attracted toward the positive electrodes. So, it will acquire a velocity, propulsion velocity u e. So, so now this because of this now this because of these free ions around the particle, so things becomes bit complicated. Now, these ions also will get a Coulomb force due to this applied electric field, and they will also migrate. And another thing is that the particle is moving, so there will be a wake formation. So, the fluid will be dragged downwards. So, that means along with that ions, so that will be pushed backward. So, downstream motion will be occurred. In addition, the ions which are imbalanced ions will acquire Coulomb force, and they will be dragged towards the electrodes, to the respective electrodes, and in a process they will also drag the fluid, because these ions are dissolved in the liquid medium. So, in that way there will be a complicated situation will arise. Okay. So, our intention is to model this kind of situations. That means, what we have is a charged particle, colloid particles, that means a particle of micron size or nanometer size is submerged in a polar medium where there are ions are ionic solutions. It is dissolved in an ionic solution and subjected to an applied electric field. So, this kind of situations we would like to study now. Now, for a simple situation, say suppose if I forget about the medium as let us assume that it is a perfectly dielectric, no free charge, no ions are containing. So, and the particle have a say a charge as Qs is the particle charge, and the electric field applied is E0. So, the electric force which will be experienced by the particle is Qs E0. Okay. Now, Qs E0 provided we are considering that surrounding the medium in which the particle is suspended have no free charge or free ions, imbalanced ions. So, the electric field is E0 and charge is Qs. So, it experiences the electric force Fe. So, because of that the particle will move. So, let the particle u is the velocity of the particle, So, now since the particle is moving, so and let us assume the particle is moving with a Stokes velocity. So, it will experience a drag. The particle is moving in a medium, so it will experience a drag, and that drag let us call that is the Stokes drag is given by 6 pi mu a u e. Mu is the viscosity of the medium, is the fluid viscosity. Now, if the electric field is the only mechanism, so then at steady state what we should have, if there is a steady propulsion, these forces will be balanced. So, at steady state situation, that is Fe minus Fd should be 0, net force will be 0, because there is no acceleration. So, that is the thing we have stated here more clearly. So, this is the particle experiencing a electric force. Particle will translate under the influence of the electric force acting on it. Since there is no unbalanced charge in the dielectric fluid, there will be no flow of this fluid under the influence of uniform external electric field. That means, the Coulomb force is 0, no electroosmotic flow occurs as the electric body force is 0 everywhere in the fluid. So, the particle is moving with a velocity u e. So, it will experience a drag. Since it is we are assuming that velocity is very low velocity, that is with the Stokes regime. So, the Stokes drag can be expressed as given by this way 6 pi mu a u e. A is the radius of the particle. So, there is no acceleration. So, this electric force and the Stokes drag will be balanced, and it will be given by F e minus F d equal to 0, and from here we can find out the velocity u e, the propulsion velocity of the particle, which is given by charge containing the charge amount of charge containing by the particle, the external electric field, and this 6 pi mu e a. Now, another important parameter or important measurement we make is the electrophoretic mobility. So, that means, the electrophoretic mobility, which is defined as the electrophoretic velocity per unit electric field. So, that means, mu e is defined by u e by u 0 E 0. E 0 is the applied electric field. So, that becomes Q s by 6 pi mu a. This implies that a positively charged particle moves along the direction of the applied electric field. So, if Qs is in the Qs is positive, so it will move in the along the direction of the applied electric field E0, and if Qs is negative, so it will have a opposite direction depending on the Qs charge. So, it will move on the along or reverse direction of the electric field. So, this is the simple situation where we have taken the surrounding or the medium has no free charges. Now, when there is a free charge in the medium, so then things becomes complicated. Now, this capillary electrophoresis, that is normally is used for sorting and characterizing the particle. So, basically what it is done in a capillary tube filled with electrolyte or other mediums, later on we will talk about gel medium also. So, in which the particle is suspended and the electric field is applied across this capillary, and a electrophoretic velocity is developed. And of course, as we could see from the previous one, you see these depending on the charge or the radius, velocity will differ. So, now we can sort the particle in terms of their velocity, in terms of the size, charge density. So, this kind of technique can be applied in capillary electrophoresis. That is why it is very helpful. Also, the experimentally one can measure the electrophoretic velocity, and through that one can find out the charge, what is the electrostatic characteristics of the particle. So, that means we know the particle electrophoretic velocity, through that we can get a expression for the charge density it contains and the other electrokinetic properties of the colloid particles, which are also sometimes very important in biomedical applications. So, normally these capillary wall are quite far off, say like it will be like 25 micrometer or 50 micrometer radius. So, if I consider a particle of size, even if it is a 1 micrometer radius, so that means this distance quite large. So, wall effect is negligible. Now, if I do the mathematical model for that, so now before that the previous expression whatever we have derived for the electrophoretic velocity was derived under the assumption that there is no unbalanced charge in the fluid. However, when a charged particle is in contact with the electrolyte solution, an electric double layer will form. The unbalanced counter ions in the double layer will experience electric body force in presence of an external electric field. That is the Coulomb force what we said. The ions will migrate and modify the electric field. Now, the ion distribution will be distorted, and in that way there will be another induced electric field, and that will go in the opposite direction. So, mostly this will be the retardation effect. Okay. Thus, the presence of the double layer will modify the distribution of ions and electric field, which in turn will modify the electrophoretic velocity of the particle. So, schematic diagram is shown like this way. So, if we have a diffuse layer, so that means there is a imbalanced ions. So, when there will be an electric field is applied, so these imbalanced ions will acquire a net body force, and it will drag the fluid, and also the ion distribution will be distorted, and that creates an induced electric field. And so, whatever the formula we have developed in previous slide is no longer valid. Now, if I want to do the full mathematical situations, so I can write the equations whatever we have already derived. This is the Navier-Stokes equation modified with the electric body force. So, rho e is the charge density at any point within the fluid. So, within the electrolyte in this case, because we are taking a ionized fluid. So, there is a we are scaled the variables. So, we get a Navier-Stokes equation of this form incompressible. So, this is the continuity equation and this is the Nernst-Planck equation corresponding to the ith ionic species. So, Pi is the Peclet number depending on the diffusivity of the ion and this is the convective transport, diffusion of ions, electromigration. Phi is the electric field. Now, this electric field are contributed in both ways by external as well as the redistribution of the ions. So, this electric field satisfy this equation, Laplace equation, which comes to the Gauss law given by this way. Now, the external electric field always satisfy delta phi external electric field. If I call psi, so it will be always delta phi equal to 0. So, that means to describe mathematically the electrophoresis of the particle in a electrolyte medium. So, we need to can be described by this set of equations. So, we need to compute or solve this set of equations. So, these equations are coupled. Now, depending on the coordinate system, if it is a spherical particle, so we can use a spherical coordinate system and we will have 3 components and also 3 components for the momentum equation and then 3 depending on the number of ions. So, if it is a Z-Z symmetric electrolyte, so we will have 2 ionic species. So, we will get a 2 equations for the ion transport. Again, it is coupled with the velocity field and of course, the velocity field is coupled with the electric field phi and the charge density rho e. Rho e, as you know, is the net charge density. So, rho e is sigma z I n I, whatever we have already discussed before. So, this set of equations need to be solved if we have to describe the motion. Now, here the scaling, we can take the scale velocity scale given by this one. This is the well known that Smolchowski velocity. If phi 0 is the potential, so phi 0 is the thermal potential RT by F and the electric field is scaled by this manner, capital lambda, and there are 2 parameters appearing. One is the Reynolds number, although it will be very small, so one can neglect the Reynolds number situation. In fact, we have neglected here the convective terms in the inertia terms is already neglected. So, the Reynolds number is based on the velocity u 0, the viscosity of the medium and the length scale A, and R is the Reynolds number and Peclet number. Now, the boundary conditions. So, we can put on the surface of the particle the boundary condition as 0 velocity and ion impermeability condition, that means flux of ions is 0, grad n I is 0 over there. Imposed particle can have either a uniform zeta potential, either I can say phi equal to 0 or del phi del r equal to sigma, epsilon E del phi del r equal to minus sigma, that form already we have described. So, these conditions either in terms of constant zeta potential or constant surface charge density, and far away from the particle, that means where the presence of the particle are no longer important, we can impose the condition that the fluid is moving with a velocity u e and phi, the electric field is merged with the external electric field lambda r cos theta. R is the radius at which we are measuring and n I equal to 1. Now, here what we did is, here basically we keep the particle stationary. That means, we have taken a relative coordinate system. That means, the particle is kept stationary and fluid is assumed to move forward, move towards the particle with a velocity u v. So, that is why this condition minus u v. So, this is analogous to the situation. So, basically the situation is the particle is moving with a velocity u v. Now, if I consider the moving frame of reference, which becomes mathematically complicated. So, that is why what we did is we kept the origin, we consider the origin at the center of the particle, and we consider the particle is stationary and the fluid is allowed to move with a velocity minus u v from the far away distance. So, this is the equivalent way of presenting. Now, what we need is, by solving the velocity and charge density and all and the electric field, what I need is the force balance. Now, forces are electric force and the drag. So, electric force are given by the Maxwell's stress tensor given by this equation, and the drag, the hydrodynamic drag, that is due to the viscous force and the pressure drop. So, that is governed by that sigma h term. So, the Maxwell's stress tensor can be expressed in the form as written over here, and the drag is due to this pressure and surface pressure and viscous shear stress. So, once we have the electric field and the velocity and pressure, so one can theoretically obtain the electric force and the drag. So, for a stationary situation where the particle is moving, translating under the action of the electric field. So, what we will have is F e plus F d to be 0. So, F e plus F d should be balanced. So, now what procedure normally is done is that this u e we cannot put as a here, this boundary condition u e is not known. So, what we do is it is unknown. Okay. So, what we do is a iterative process. So, that means you solve this iteratively by this manner, start with a initial approximation for the electrophoretic velocity u e, some initial guess, and through that we compute this F e f d, then calculate the next iteration iterated value by this manner, and then again go back, solve the Navier-Stokes equation, Poisson Navier-Planck equations, and the electric field equations, all coupled manner, to get the modified velocity, and then calculate the drag. So, if we have established a 0, then we stop the iteration, otherwise we proceed further. So, this is the general form to find out the electrophoretic velocity, which obviously undoubtedly a very complicated is a complicated one. I will not say very complicated, because through the computer simulations can be done. So, it has been done for several authors. So, one can do that. Now, first let us talk about the limiting situations. So, that means when we have the case that Debye layer is very thick. So, Debye layer is very thick. So, in that case what we can assume that limiting case is, so Ka is very low, thick Debye layer. So, if we neglect the deformation of the electric double layer in this case, then under a symmetry condition in the angular direction in spherical polar coordinate. So, that means what we consider is only the dependent variable is only independent variable is the r, only variation in the radial direction. Then the Poisson equation for electric field can be expressed as epsilon E 1 by r square ddr of r square d phi dr equal to minus rho e. If ions are, so this is the form of the Poisson equation. Now, if the ions are assumed to obey the Boltzmann distribution, so we assume that ions are following the Boltzmann distribution. So, what I get is so in that case what we can write is epsilon e. This kind of equation we have already done several occasions. So, I can straight away write this is becoming 2 f c 0 sin hyperbolic f phi by r t. Now, if I apply the Debye-Huckel approximation, Debye-Huckel approximation in this case, so that means this nonlinear equation we linearized. So, this can be written as epsilon e 1 by r square d d r of r square d phi dr equal to 2 f c 0 by r t phi. Okay. So, let us define the Debye length, inverse of Debye length as 2 f square c 0 by epsilon e r t. So, and so what I get, this equation is becomes 1 by r square d d r of r square d phi dr equal to k square phi. Let j equal to r phi. So, what I get if I substitute now, so what I get is d 2 j dr 2 equal to k square j. So, solution is very simple. We can write j equal to a to the power minus kappa r plus b to the power kappa r. Now, what are the boundary conditions? So, the boundary conditions what we have is we can say that as r tends to infinity, phi is tending to 0. That means, here phi is the equilibrium double layer potential. So, phi is tending to 0. So, this implies that is 1, and r equal to a, you have phi equal to zeta. So, with that we get the expression as zeta a by r exp of minus kappa r minus a. This is the double layer potential. So, this which is the double layer potential, Of course, here we assume that electric field is weak. Now, on the surface of the particle, minus del phi del r equal to sigma s by epsilon e at r equal to, this is at r equal to a. Sigma s is the surface charge density. So, what you get is from here sigma s equal to minus epsilon e del phi del r at r equal to a, and so this can be obtained from here. So, this becomes sigma s becomes, if I do little algebra at r equal to a, one can find out that I am skipping this. epsilon E A plus epsilon E zeta kappa. So, that means sigma s is basically can be obtained as zeta epsilon E by A into 1 plus kappa A. Okay. So, this is the surface charge density. Okay, now we will continue into the next class.